Okay, this is basically 7.4 part 2. Talk about graphing and the logarithmic and exponential. So let's go back to 2 to the x. This is an exponential function. If x is negative 2, y is 1/4, right? 2 to the negative 2 means 1 over 2 squared, that's 1/4. 2 to the negative 1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8. And I get a function, a graph that looks like this, y equals 2 to the x. Well, now let's look at log base 2. I'm going to zoom out a little, I guess. Log base 2 of x equals y. So remember, this is 2 to the what equals x. So I want to know 2 to the what equals 1/4. Well, I'd have to flip it and square it. So I get negative 2. And then 2 to the what equals 1/2. That'd be negative 1. 2 to the what equals 1. Let me zoom back in again. So 2 to the what equals 1/4. That'd be negative 2. 2 to the what equals 1/2. Negative 1. 2 to the what equals 1. 2 to the 1 equals 2, 2 squared equals 4. Again, so notice how I'm using the definition. I'm looking at it backwards. I'm not really worrying so much about log base 2 of x is what? Log base 2 of 1/4 is what? I'm just really thinking about it as 2 to the what equals 1/4. It's just so much easier to think about it in its translation. And then notice what happens, that these negative 2 1/4 becomes 1/4 negative 2. Negative 1 1/2 becomes 1/2 negative 1. That is the nature of an inverse function. These x and y values get reversed. So when x is 1/4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. When x is 8, y is 3. So when you invert this, you get a graph that looks like that. This doesn't cross the x-axis. This doesn't cross the y-axis. This has a horizontal asymptote. This has a vertical asymptote. And my graph doesn't look so, because again, there's no way that x can ever be negative, because I can't raise something to a power and get a negative number. It's just not going to happen. Basically, this should be a translation of a reflection across the line y equals x. Mine doesn't look so great, but that's essentially what's happening in an inverse function. So again, I think graphing a log is easier to think about it in its translated form. But these are what logarithmic graphs look like. And they can be shifted and stretched and flipped and all that good stuff, just like you guys are familiar with. A couple of the problems ask you to find the inverse. Well, here it says y equals 6 to the x. So the first thing I'm going to do is translate this into the log version. So remember, 6 to the what equals y. So 6 to the what equals y. Log base 6 of y equals x. I'm going to use the definition to translate this statement. And then I'm going to switch x and y. So this becomes log base 6 of x equals y. So there's my inverse function for that. So this equation A is the inverse of this equation B. Which means then that if I put this in for x, I would get x. We're going to talk about this in a minute. Which makes sense though. 6 to the x equals 6 to the x. Remember, that's the definition of an inverse function. If I called this, I'm a little out of sorts here, sorry. This was f of x, and this was g of x. Remember, if I put f of x into g of x and get x, I've got an inverse, which is what happened. In this case, y equals the natural log of x plus 3. If you're given something like this, you can just go ahead and switch x and y. And then now I'm translating it. What does this really mean? This means e, I'm in a logarithmic natural, the natural log, e to the x equals that. So then I write this, e to the x equals y plus 3, and then I just subtract 3 from both sides, so y equals e to the x minus 3. And again, kind of complicated. If I plug this into there, I should get x. So ln e to the x minus 3 plus 3 would give me ln e to the x. And what does this mean? Again, it means e to the what equals e to the x. Well, e to the x equals e to the x. That's a little complicated. You're going to probably have to just follow the algorithm on that. In this case, translate it to a log and then switch x and y. In this case, if it's already in a log, switch x and y and then translate it to an exponent. And this idea, these two are sort of good to know, and some people use them to undo logs and exponents. I tend to use the definition. More on that again later. So here's example 5. And this is this idea of a log undoes an exponent and an exponent sort of undoes a log. But again, I'm going to use a definition. So I'm just going to call this, and you'll learn this in calculus, I'm going to call that u. So if I let log of 4 be u, now I can rewrite this as 10 to the u equals what? And remember, this is 10 to the u equals 4. So if you translate this, so I thought this looked a little complicated, 10 to the log of 4. So I said, well, let's consider log of 4 to be u. So really what I'm looking at is 10 to the u. What could that possibly be equal to? Well, then if I go back up here and translate my statement, 10 to the u equals 4, oh, I know, 10 to the u equals 4. Thinking back on this idea of inverses, if I have 10, to the log of 4, again, what's my base here? 10. So this is saying 10 to the what equals 4. Well, if I raise 10 to that value, I am going to get 4. Either way, I think it's a little funky to think about, but again, I don't use this property very often. You'll see why later. So what's going on here? Since I already have an x, I'm going to call this question mark. So this is saying 5 to the question mark equals 25 to the x. Well, what would I have to raise 5 to get 25 to the x? Well, I know this is 5 squared raised to the x, which is just 5 to the 2x. So my question mark must be 2x. Log base 5 of 25x is literally 2x, because 5 to the 2x equals 25 to the x. That makes sense. 5 squared is 25. Raise it to the x, 25x. Do what you can with those. They take a little bit more practice, a little bit deeper understanding, but notice I keep going back to the definition. 5 to the what is 25x. Over here I went back to the this definition. I turned this into a statement and then rewrote it. 10 to the u is what? Oh, literally that's what I have. 10 to the u equals 4.